Let's look at some of the circle theorems. So some theorems are based on angle properties. Now the first theorem is about the angle subtended by an arc at the center and the remaining part of the circle. So in this diagram, let's say that AB is one arc, and if I join the radius OA and OB, I have one angle at the center, which is angle AOB. So we have one angle at the center which the arc AB is subtending at the center. Now the same arc AB can also subtend an angle at the remaining part of the circle. So if I exclude the arc AB, I have this entire uh, portion of the circle remaining. So if I choose any point, let's say I choose point C, then I am making angle ACB at the remaining part of the circle, angle ACB. And this theorem states that the angle at the center, which is angle AOB, will be twice the angle subtended at the remaining part of the circle. So in this situation, angle AOB will be equal to 2 times of angle ACB. Or if I say that angle ACB is x, AOB will be 2x. If I give example with numbers, if I say angle ACB was 40 degree, then AOB will be 80 degrees. And let's look at one animation to see all the possibilities. So if you see here, angle BOC is the angle subtended at the center, which is 80 degree, and angle BAC is the angle at the remaining part of the circle, which is 40 degree. So the angle at the center is double the angle at the remaining part. I can also change the measurement. So let's say now I'm changing to BOC 100 degree, then BAC is 50 degree. I can also look at moving point A anywhere on the remaining part of the circle. So the relation is still the same. That the angle at the center BOC is 100 degree and the angle at the remaining part of the circle BAC is 50 degree. So angle at the center is always double. Let's look at the next theorem. Okay, so this theorem, if you want to know the statement, this is the statement. Angle that an arc of a circle subtends at the center is double that which it subtends at any point on the remaining part of the circle. Also, just to give another context, the arc that we are talking about in this scenario, that arc can be a major arc also. For example, here AB, I am taking the major arc AB, which is more than half of the circle. Then if I look at what is the angle subtended by major arc AB at the center, it will be the reflex angle AOB. Reflex angle is any angle which is more than 180 degree. Okay, so angle AOB in this case is reflex, and then the angle subtended by the same major arc AB at the remaining part of the circle in this situation is angle ACB. So then reflex angle AOB is the angle at the center. That should be double the angle subtended at remaining part of the circle. So if I take some numbers, for example, if I say angle ACB was 120 degree, then the reflex angle AOB will be double of 120, which is 240 degree. And we can also look at the animation again. So here, if I extend this like this, if I make BC as a major arc. Now here BC is the major arc. The angle at the center is reflex angle 220 degree. And then the angle at the remaining part of the circle BAC is 110 degree. So still the angle at the center is double the angle at the remaining part of the circle. Okay. Then the next theorem is about angles in the same segment of a circle. So let's consider the segment or even the arc AB. Segment is anyway the region between the arc and the chord AB. So let's say this is my minor segment AB. So this is making an angle, let's say ACB. And it's also making another angle which is ADB. So then, according to the theorem, angle ACB must be equal to angle ADB. Or I can say angles in the same segment of a circle are equal. We can think of the logic something like related to the previous theorem, angle ACB, and if I look at angle AOB. ACB and AOB, according to the previous theorem, angle AOB will be 2 times of angle ACB. And even angle AOB will be 2 times of angle ADB for the same reason. So then I can say that 2 times of ACB is same as 2 times of ADB. Therefore, ACB must be equal to ADB. So for example, if ACB was 40-degree angle, then ADB must also be 40-degree angle. So let's look at the animation once. So let's say in this situation, I have arc AB subtending angle 35 degree at different points in the circle. If I let's say increase the length of arc AB, the angle subtended will also increase. So let's say now I'm increasing it to like this. Then you see that the angles in the same segment as it is in AB, they are all 50-degree angles, and the angle at the center as expected is 100 degrees. Okay. Then similar to the theorems that we have seen, in case I look at a semicircle is half the circle, and the diameter of the circle will divide the circle into two semicircles. Now, if I consider the arc AB, which is exactly dividing the circle into two equal parts, then the angle subtended by arc AB at the center in this situation will be exactly 180 degrees, because AOB will become a straight line, and the angle in a straight line is 180 degree. Now, if I apply the first theorem that we learned today, that the angle subtended at the center is double the angle at the remaining part of the circle. Then if I look at angle ACB, it is the angle subtended by arc AB at the remaining part of the circle. So AOB will be 2 times of angle ACB. And I know that AOB is 180 degree, so ACB has to be 90 degree. So I can state this theorem as angle in a semicircle is a right angle. So these are the three angle properties. Next, we have some cyclic properties. So cyclic properties is about the properties of a cyclic quadrilateral. So quadrilateral is any polygon with 4 sides. I will call a quadrilateral as a cyclic quadrilateral if the 4 vertices of the quadrilateral are on the circumference of a circle. So for example, in this figure, ABCD is a cyclic quadrilateral because the vertices A, B, C and D are on the circumference of a circle. So one property is that the opposite angles of a cyclic quadrilateral are supplementary. Supplementary is when any two angles add up to 180 degrees. So here the opposite angles are angle A and angle C. Another pair of opposite angles are angle B and angle D. So they will add up to 180 degree. So if I wanted to give example with some numbers, let's say angle A was 80 degree, then angle C will be 100 degree. They will add up to 180 degree. or let's say angle B was 70 degree, then angle D has to be 110 degree, like that. And again, if you want to see an animation, so this is a cyclic quadrilateral. So the opposite angles are labeled here, alpha and beta. Here they are 80 and 100 degree. If I just move the points around, the measure of the angle is also changing. And for example, in this situation, we see that if one angle is 120 degree, the opposite angle is 60 degree. So 120 plus 60 is adding up to 180 degree. All right. And then the last theorem is about an exterior angle of a cyclic quadrilateral. So I can extend any one side of the quadrilateral and I will get an exterior angle of the quadrilateral. Here I have extended the side DC so that I am getting the exterior angle for C. So according to this theorem, the exterior angle will be equal to the um, opposite interior angle. So if I look at interior angle C, its opposite angle is angle A. So exterior angle C is equal to the interior angle A. If I had taken some numbers, for example, let's say exterior angle C was 70 degree, then interior angle A will also be 70 degree. The reason being, the if I look at angle C, the interior angle C and exterior angle C, they are on a straight line. So they form a linear pair. They will add up to 180 degrees. So if exterior angle C is 70 degree, interior angle C will be 110 degree. And then if I look at the previous theorem that opposite angles of a cyclic quadrilateral are supplementary. So angle C, I'm talking about interior angle C, and interior angle A will add up to 180 degree. So that's the reason why angle A has to be 70 degree. So these are all the angle and cyclic properties of a circle.